Hello students and welcome to part 7 of our video series. So last week we covered simple circuits, so we kind of got an idea on how to solve circuits. This week we're going to be moving on to Kirchhoff's rules. This is another way to solve circuits. So it's basically the same idea. We kind of want to know the current that is going to go across the circuit. We're not really going to be focusing on voltage, but if you have the current, you could also calculate the voltage on the resistor. But this week we're going to be focusing on solving some more complex circuits. However, we're going to be using Kirchhoff's rules. So to begin, let's just define what Kirchhoff's rules are. And it's fairly straightforward. There's two rules, the loop rule and the junction rule. Now again, this week you're going to be filling out tables, so you're going to be given the resistance, so this is going to be known. And then you're going to go into your simulation and you're basically going to measure the current for each resistor, and you're going to fill it out here. And then kind of like last week, we're going to do some calculations using these two rules to find a theoretical value, and then you're going to take the percent difference between those. So this week you don't really have to draw the circuits out and simplify like we were doing last week. Because we are going to be using Kirchhoff's rules. So basically the only thing that you're going to need to look at is just your main circuit. I'm going to work out and show you some examples on how to apply these rules. But basically the loop rule assumes conservation of energy, right? So the loop rule says that the potential difference, or the delta V, will be 0 for the said loop, right? Basically what it means is, like, let's say this is 5 volts here. So if this is positive 5 volts here, if you go all the way around, you know that this side is negative. This is going to be negative 5 volts. You add those two things together, it equals 0. So that's the idea of the loop rule, is conservation of energy. So we're going to be using this loop rule to basically go through our circuits and come up with different equations and so forth, so we could calculate the current. It's going to be more apparent when I show you guys examples, but just keep that in mind, that the loop rule is based off of conservation of energy. And we kind of saw that last week when we were doing the simple circuits, right? The parallel circuits and so forth, and the series circuits. You might have noticed that in the series circuit, when we had our resistors in series, and you calculate the voltage, if you add all the voltages up, they added up to your they should have added up to your power supply, right? So it's just exploiting those rules, or conservation of energy. Now the junction rule, we kind of saw that last week too. You might have remembered, like in the parallel circuit. Remember when we calculated our equivalent current? I might have mentioned in the video that when you're in a parallel circuit, if you add all the little different currents up, that they should add up to your equivalent current, right? So that's basically the idea of the junction rule. So we're going to apply these two rules. Now when you're solving the circuits this week, you have to use Kirchhoff's rules in order to get credit. By drawing your circuits and simplifying them down like we did last week, yes, you could solve the circuits that way, but you won't get credit for this lab if you solve them that way. You must use Kirchhoff's rules. So I'm going to go through how to set up these circuits and solve them using Kirchhoff's rules in the next few slides. So I'm going to give you 4 examples, and it should help you get through your lab. There's a few different ways you could apply these rules, but I'm going to try to make it in a way where it looks very clear and simple, especially if you don't have a very strong algebra background. So let's begin with the first example, right? So the idea is we're going to want to fill out this table, and the main idea of this is we want to know the current across each resistor. So we want to know the current here, here, and here, okay? And we're going to eventually fill out this table. So here's example 1. We have a circuit that is series parallel. We know it's in series because it's going right here, but there's a junction, and these two resistors are in parallel, okay? So there's basically 3 steps to solving these circuits. This is the order that I find should be the most simplest when applying or when solving these circuits. So step 1 is we always apply the loop rule. Step 2, we apply the junction rule. Step 3, we apply our knowledge of simple circuits. Now, we could kind of go out of order in these steps, but I find that if you approach these circuits in this way it makes the math a little bit easier, and it makes it easier to understand the circuits. So if you're solving these circuits in your physics class already and you're not doing it in this order, that's okay. But this is the order that I feel makes the most sense. So these are how I list the steps. So step one is we apply the loop rule. Okay. So what is the loop rule? That basically means that we're going to be looking at the circuit, and I always start by locating a battery. In this case, I see the batteries right here, and I go around a circuit and I start labeling, right? So I'm going to come up with one equation, right? So the current's going to travel, it's going to hit, I'm going to go do this loop right here. So it's going to travel, it's going to hit, and I'm going to have I3, R3. I hit a junction, and it could go right on the junction, so my equation would be I3, R3 plus I2, R2, and it comes back around. So there's one equation, okay? We could also come up with another equation, right? Which could be this, I3, R3, it goes this way, I1, R1. So these are the two equations that we could come up with when we apply the loop rule. Remember, this is in parallel, and what we know about a parallel circuit is, in this area, that the voltages are going to be the same, right? So if you add this voltage here plus one of these, it's going to add up to V1. If you add this voltage here plus this one, it's going to add up to V1. Okay? That's why, that's basically the concept of the loop rule, right? It's based off of conservation of energy. You can't add both of these because you're going to violate the conservation of energy, because there's going to be more energy, because we know with a parallel circuit that the voltage must be the same, so we can't add that voltage up twice. Okay, so that's why we could come up with these two loops. Now, one of the things I want to point out is that when you're solving these circuits, you should count your resistors, right? 1, 2, 3, right? So for each resistor that you have, you're going to have an equation for that, right? Because we're going to solve these by using systems of equations. So there's 3 resistors, we expect 3 equations. Typically, you'll get one equation from the loop rule, you'll get another equation from the junction rule, and the rest of the equations you're going to get in step 3. Now, you could come up with different equations and solve these in different ways, right? So the equation that I'm going to choose to use from the loop rule is going to be this one right here, okay? So now I have one equation. What I'm going to do next is I'm going to apply the junction rule, which says that the current going into a junction right here is going to be the same as a current going out of the junction. So you can think of this like a water hose. Pressure's going in, some of the water's going this way, some of the water's going that way. It recombines and it becomes the same, right? So the current right here, we named the currents after our resistors. So this is resistor I3. So in this area, the current will be known as I3, okay? So we'll have I3 will be equal to the current of I1 plus I2. That is known as the junction rule. So we have I3 is equal to the current of I1 plus I2. So here's our second equation. So now we're going to do our third step, which is applying our knowledge of a circuit. Now I already mentioned this before. This part is in parallel. What do we know about a parallel circuit? The voltage is the same, right? So we have I1 times R1 is equal to your voltage through Ohm's law. Remember, Ohm's law is V equals IR. Okay, so we could say I1 R1 is going to be equal to I2 R2 because the voltage is the same. So let's just make up a number. If this is 2 volts here, it's going to be 2 volts there. All right. So that's how we get our last equation. I1 R1 is equal to I2 R2. So now you know that we have 3 equations. 1, 2, 3. We have 3 resistors. 1, 2, 3. So now we're going to solve this by using the algebraic approach of solving by a system of equations, right? So we're going to solve by using a system of equations. So if you're not really too good at algebra, that's okay. I'm just going to break it down for you again. So basically when you solve through a system of equations, for our purposes, we're going to look at our loop equation, right? And we're going to ask yourself, what can we get everything in terms of to solve this, right? So I chose to use this equation. So I have this I3 here, and I see an I2. So I'm going to want to solve this for I1. I know that sounds confusing, but what I'm going to try to do is get everything in terms of I2. I see an I2 here, so I want to see I2s everywhere. It'll make more sense after we solve these, but just keep that in mind. We're going to try to get everything in terms of I2. So the first thing I'm going to do is I'm going to solve this equation for I1. So I have I1 is equal to all of this junk right here, right? So now that I have my I1, I'm going to take this I1 and I'm going to plug it into this equation. So now we have I3 is equal to all of this plus I2. Now you see that we have I2 here and I2 there. So we're on a good track of getting everything in terms of I2. Now we have to take this equation and plug it into this right here. So now we're going to take this and plug it into the I3. And now we're left with everything in terms of I2. So we have delta V is equal to I2 here, there's I2 there, there's R3 and I2 there. Now you might notice that everything in this equation is being multiplied by this I2. Because of that, we know that we could factor out this I2. So that's going to be our next step. We're going to factor out the I2 and we're going to have an equation that looks like this. All right. So now we're pretty much done, right? We pretty much solved everything that we need to do. What we could do now is we could calculate this numerically with the calculator because you're going to be given R1, R2, and R3. So you know the values of all your resistors. So you could plug all these values into your calculator right here, right? And you're going to calculate some number. I'm going to let you all calculate that number and use the resistors values, but I'm just going to use this symbol to represent that number that you calculate. So you plug this into your calculator and you calculate some number, and now once we have that number, we could divide it by the voltage that we're using in our circuit, right? So they're going to give you this value too. They could say 5 volts, 10 volts, 100 volts, whatever that is. You know the voltage. So you're going to take that number, or you're going to take your voltage and you're going to divide it by that number, and then you're going to know the value for I2, right? So once you get that value for I2, you plug it in to your table for I2. So once you have that, you have the values for all your other currents, right? Because once you know I2, you're going to know I1 because you're going to plug the value in for I2 here and you're going to calculate I1. So you put I1 there. Once you know I1, right, and I2, then you're going to come back to this equation. I1 plus I2 equals I3, and then you calculate that and you plug it into your table. So this is the main setup or the main process of solving these circuits, right? So we're going to solve these circuits by doing a system of equations. Now, in the later examples, I'm not going to show you how to go back and or give you, you could do it yourself, but you should understand that what we're going to be doing is we're going to be trying to get at least to here, right? Or understanding how do we get to here so we could do our calculations and relate everything. So I find if you follow this 1, 2, 3 step order, it makes your work look neater, cleaner, and you could kind of understand, right? Because you're kind of always working back to this loop rule equation because some of these get a little bit more complicated, right? Especially when we start adding resistors. So like here's an example of it getting a little bit more complicated, right? So in this example, we have an additional resistor, right? So we have 1, 2, 3, 4. So we're going to expect to see 4 equations, right? So we're going to do the 1, 2, 3 steps again, right? So we're going to apply the loop rule. And just to get you familiar with applying the loop rule, I'm going to show you all the different loops that you could have, right? So we could apply the loop rule and we could say, hey, we're going around this loop. This is in series, and all these 3 resistors are in parallel because there's a junction, right? You can identify a parallel circuit with the junction. So you look for those little dots and always kind of take your little cursor and go around the circuit and like, oh, wow, I could go this way and that way. That's how you know you're at a junction, like a crossroad. So that tells you that this is in parallel. Now, if you take your little cursor from your battery, and it could be from the positive or negative side, and you hit a resistor first, that's how you know that this resistor is in series, right? So this is in series with this parallel circuit. So this is another series parallel circuit. So we know there's a junction here and a junction here. So all these resistors, 1, 4, 3, and 2 are in parallel, and then this is in series with that. Okay. So one of our first equations that we could get is this, right? We hit I1 R1, right? Because this is a series portion, and it could go this way. I2 R2. Another equation that we could get is I1 R1, right? This is in series, it goes this way, then it turns this way, and it could be I3 R3, right? And then the last equation we could have is I1 R1, and it could be I4 R4, right? So that's how you apply the loop equation. You could use any of these three equations to solve the circuit, right? So your answers may be different than mine, and that's okay. Now, me personally, I like to choose the middle loop because I just feel like this works out, it looks a little bit neater. So this is the equation that I'm going to have. Now, typically, when you apply the loop rule, you're only going to be using one equation, at least for the circuits that we're going to be dealing with. So this is going to be the equation that I'm going to use for the loop rule, that middle loop. So we're going to go around and that. Remember, the voltage in a parallel circuit here, here, and here is the same. So basically, if this is 5 volts and this is 2.5 volts, then we know that 2.5 volts is on this resistor plus 2.5 volts on that resistor equals 5. 2.5 here plus 2.5 there equals 5. We could do that, and the loop rule is set in a way to not violate conservation of energy, okay? So that's why we pick one and we can't add more resistors. So that's why we don't add everything. We're adding whatever in that loop, all right? Because it's based off of the conservation of energy. Now, remember step 2 is going to be the junction rule. So we're going to identify our first junction, and you always go from your battery. You can go this way or this way. But you see that I have a junction here. And this junction, the first original current is going to be named after this first resistor, I1. So we have the current I1. So this current I1 is going to be equal to whatever's going in, right? So it's going to be equal to I2 plus I3 plus I4, right? Because the current's going to split up. Someone's going to go this way, someone's going to go over here, and someone's going to go over there. And we know that all our current is going to add up, right? So this is based off the idea of conservation of charge, right? So we have our charges flowing through the wire. Some of the charges is going to go one way, some of the charges are going to go another way. They all have different currents, but all those currents, when they come back, you can think of like the pressure is getting back higher again. It's going to recombine, and it's going to be back at its original current. So this is based off the idea of conservation of charge is a junction rule. So this is how we come up with this equation. So now we're doing pretty good, right? We have 2 equations, but we still need to come up with 2 more. Again, this is where we apply our knowledge of circuits. For this case, we know most of the circuit is in parallel, right? And like I said before, what do we know about a parallel circuit? Is that the voltages are the same, meaning that the voltage here is the same as here, and the voltage here. So all the voltages is the same. So we know from Ohm's law that when we multiply our current, like I4 times R4, that equals our voltage, right? So we could say that this one is equal to that one, this one is equal to this one, or this one is equal to this one. There's several combinations we could come up with. Now, I always like to pick one in the middle, and because that's what I like to do. So I'm going to pick this equation. I'm going to do I3 times R3 is equal to I2 times R2. I just feel like it simplifies when you pick things in the middle. I'm going to say that I3 R3 right here again is equal to I4 R4. So these are the 2 equations that I'm going to use, right? And this is basically saying is that the voltage here is equal to the voltage there, the voltage here is equal to the voltage there. Okay, so now we're in pretty good shape, right? We have 4 resistors, and now we have 4 equations. 1, 2, 3, 4. And the rule, the algebraic saying that we always say is that for each unknown, you should have an equation. So there's 4 unknowns, 4 currents that we need to know, and now we have 4 equations. So now it's algebraically possible to solve this by using a system of equations. So we have 4 resistors, 4 equations, okay. So now we can ask ourselves, what do we want to get this in terms of? Now you see that I have an I3 here, and then there's some I3s here. That's why I chose that middle one, because it just makes me feel a little bit more comfortable. What I want to do is I want to get everything in terms of I3, all right? So this is pretty easy to see. This I1 is going to go in here, and I see I3 there, so that means I need to solve for I2 and I4. So that's what we're going to do, right? We're going to solve these two equations right here, and I'm going to solve them for I2 and I4. So here's me doing it for I2, and now I'm going to do it for I4, right? And just like before, what we're going to do is we're going to take these two, and we're going to plug it into that junction rule equation. So I2 is going to go here, I4 is going to go there. We're going to plug it into the junction rule equation, and now we could write it as this, right? Now that we have it into that junction rule equation, we're going to take this I1 and we're going to plug it into the loop rule equation. And it's going to look like this, right? So here that is times R1 plus I3 R3. So now we're in real good shape, right? There's I3 here, I3 here, I3 there, I3 everywhere. Everything's being multiplied by that I3. So now we could start doing the final steps, and that is factoring. Just like last time, we factored it out. We're going to factor that I3 out. And then, just like I told you last time, you could plug all these values into your calculator, and you could solve this, and you could get some numerical answer. And then you could take that numerical answer and calculate I3. Once you have I3, you get everything else, right? Because you go back. Once you know I3, you pick the equation that is related to I3. So you plug them in here. You get I3, you get I2, right? You get I3, you get I4. Now that you know I3, I2, I4, you get I1. So this is how you're going to start filling out your tables. So it's very important that you write down everything algebraically in all your steps, right? So in order to get credit, I must see that you're applying the loop rule, the junction rule, and you must show your algebraic work. Your algebraic work is probably the most important part, all right? So please show your algebraic work, because in order to get credit for this lab, I must see that you understand how to apply these rules, okay? And these are pretty much your circuits, right? So you could solve them slightly different. You could use one of those other two equations that I had, or you could use the equation that I used. But Kirchhoff's is probably one of the most difficult. So here's example 3. Now this one's a little bit more exciting, right? So the first thing I like to do is look at the circuits and try to ask myself what's going on. And in this circuit, just going on like what we did last time, and go from battery. I see this is in series, and now this is in parallel. But wait a minute, these two resistors are in series too. So I have a series parallel series circuit. So now we're getting to more complicated circuits, right? And there's going to be circuits that if you continue down this path, that are going to be more complicated, where you can't really say if they're series parallel series circuit. But this is a series parallel series circuit, all right? So we know that this is in series, and this area is in parallel with each other, but these two resistors are in series with each other too. So this section is parallel, and then these two are in series, and then this resistor is in series with this parallel section. So it gets a little bit more complicated, but that's what we need to start trying to do, is identifying what's going on. All right? So remember, 3 steps: loop, junction, apply our knowledge. So, I always kind of like to apply the knowledge at the beginning too, and then do the loop, but those are the 3 steps. So loop, junction, and apply knowledge. So let's apply the loop rule, right? And I'll show you all the different loops that we could go through. So here's one loop, right? We're going to go through this R1. So everything's going to go through R1 because it's the first thing from our main power supply. So we're going to have delta V is equal to I1 R1. And we could go this way, I3 R3. That's one possibility. Again, the next possibility is we could go around this. It goes this way, and we're going to go through this I4 R4. So we're going to have delta V is equal to I1 R1 plus I4 R4. It's going to go that way. And then our last possibility, which we have to be careful, is it's going to go through here, and it's going to be equal to I1 R1 plus, now this is in series. So what you should know about a series circuit is that the current's going to be the same. So the current I5 and the current I2 are the same. We could factor that out. So we'd have I2 times R4 plus R5, right? Because we basically made everything equal to I2, so we just factored that I2 out. But this is um, the last equation that you can come up with. So once you do that, um, that's how you do the loop rule. Now again, I personally always, unless it's really inconvenient, but usually it is more convenient. Personally, I like to choose the middle loop. So I'm going to choose the middle loop again, and the other two equations I'm just going to toss out and not work with. But I just want you guys to have an understanding on how do we apply the loop rule. Again, some people might use this one or whatever you like to do mathematically. If you have an algebraic way of doing things and it makes more sense to do it a different way, that's fine. But you just need to understand how to correctly apply the loop rule. All right. So this is me applying the loop rule, so I get one equation there. All right. So we got one. We have 1, 2, 3, 4, 5. So now we have to have 5 equations. So we have to find 4 more. So we're going to get another one from the junction rule. Okay. So the junction rule basically says the current going into the junction is going to be equal to the current going out of the junction, right? So this junction here, we name it I1 because this is our first resistor. So I1 is going to equal to the resistance of R3 plus R4 plus one of these currents. We can't add it up twice because that would violate the conservation of charge, because we know that the current is constant in a series circuit, just like the parallel thing that we have to be careful with. We have to be careful with the junction rule too when we have things in series. So one junction rule we can have is I1 is equal to I3 plus I4 plus I2. So I1 right here is equal to I3 plus I4 plus I2. Another thing that we can have is this. I1 is equal to I3 plus I4 plus I5, because I5 and I2 are the same. We cannot say I5 plus I2 because that would violate the conservation of charge, right? Because this area is in series. So we have to be careful. Now, because I just think it looks prettier, I'm just going to choose this equation because that's my preference. So now I have my two equations. I have 1, 2. So now we have to come up with 3 more equations. And this is where we go to applying our knowledge. And I mentioned this several times. We know that these two are in series with each other. So we know that I2 is going to equal to I5. So that's one thing that we could say, is I5 is equal to I2, or I2 is equal to I5. So that's one equation. So now we have to come up with 2 more. So now we're going to apply our knowledge with parallel circuits, right? Or things that are in parallel. So I know that the voltage here on this resistor is going to be equal to the voltage on this resistor, right? Now, you have to be a little bit more careful. I know that the voltage here is going to be equal to the voltage of this resistor plus that resistor, okay? So those are the equations that we could come up with, right? So I'll have I4 times R4, which is by Ohm's law, your voltage, is equal to I3 R3, right? Which, like I said, that's your voltage. So these two voltages are equal. Now we have to be a little bit more careful because this area is in series, right? So I'm going to say I4 times R4. The voltage is equal to the voltage of both these resistors added up. Now I used I2, right, because that was the equation that I chose. You could write I5, but it doesn't really matter. So this is the equation that I chose. So now we're in pretty good shape, right? We have 1, 2, 3, 4, 5 resistors, and we have 1, 2, 3, 4, 5 equations. So now we could solve this by using a system of equations, just like we did before, right? So now I'm going to go back to my loop equation, and I'm going to say, well, I'm going to try to get everything in terms of I4, right? That's why I always pick the middle one, because it makes it kind of easy to see. So that means I have to solve for I3 and I2, right? Because that I1 is going to go in there. So that's what we're going to do. We're going to solve these two equations for I3 and I2. So we're solving system of equations for I3, and here's it solved for I2. So now that I have these solved and everything in terms of I3 and I2, I could take these two equations and I could plug it back into that junction equation. So this I3 is going to go here, This I2 is going to go there. Okay? So now all of this is plugged into that junction equation. Now we're in pretty good shape. There's an I4 here, an I4 there, an I4 there. I4 is everywhere. That's exactly what we want. So now we're going to do our final step and plug this in to the loop equation. So we plug it into the loop equation, and now everything is in terms of I4. And now our next steps is cleaning this up by factoring that I4 out. So we factor that I4 out, and just like last time, I said it before, I'm going to say it again. You could plug all this stuff into your calculator, you could get to that numerical value, and you could take that numerical value and divide it by your voltage, and now you have I4. Once you have I4, you get everything else. You go back to these two equations, you get I3, you get I2. You get I2, you get I5, and you have all that information, you get I1. So that's how we solve these. So now let's move on to our last example. And this one, it looks a little scary for students seeing it for the first time, but I'm telling you, it's not. It's actually probably the simplest one to do. So in this circuit, you may notice that we have one battery or one power supply, and we have another power supply here. So we have two power supplies. We have a V1 and we have V2. Now, when you're doing your circuits, the sign of this does matter. So this is positive, this is positive. So they're working with each other. But the sign of these matter, because maybe if this is a plus here and a minus here, it means when you're applying the loop rule, if you're going to add or subtract. So you just have to watch out for that. That's the only danger with these. So like I said before, we're going to do the first three steps. Now, this one's a little different because we're really not going to be using the junction rule, but we're going to start off with the loop rule. So we're going to start off with the loop rule, and we'll just start off with V1. And let's go through all the loops that we could use for V1. Now remember, there's 1, 2, 3 resistors, so we're going to expect to get 3 equations. So the loop rule, we could have the loop going this way. We could have the current going where you have I3 times R3. Then it could go this way plus your battery, your V2. So here's one of the equation. Delta V1 is equal to I3R3 plus delta V2. This is this loop right here. Okay, so that's one loop. The second loop you could go is like this. Delta R3, and it's going to go up here, and it's going to be, this is in series, right? And it's worth pointing out that this could be I1 or I2, but when it's in series, we know I1 is equal to I2, so you could call it whatever you want, but it's going to kind of be like what we did on the last example, right? So we're going to write it like this. Delta V1 is equal to I3 times R3 plus I1 times R1 plus R2. And the reason why we could do this, I just factored that I1 out, is because this is in series, right? So you could write I1 or you could write I2 because I1 is equal to I2, okay? So that's another equation that we could solve. Another loop equation that we could do that's very convenient is look at this delta V2 loop. So we could write that this delta V2 loop is going through here. It's going to look like this. We're going to have delta V2 is equal to I1. Remember, it's in series again. R1 plus R2. This is a very convenient one. So mathematically, it's easier to solve this and plug it into your calculator so it's quicker. So because of that, for my loop rules, I said typically we use one from the loop rule, but this is a little special case, right, where it's more convenient to use multiple equations from the loop rule. So we're going to be using 2 equations from the loop rule. And these are the 2 equations that we're going to use. Okay. The third equation we're going to get by applying our knowledge, right? And that one I already says I1 is equal to I2. So here's our 3 equations. 1, 2, 3 resistors. We could solve it, right? And like I said, it's very convenient. In fact, we don't even have to really do too much of solving by a system of equations because this one's fairly simple, right? So what we could do is we could solve this equation, delta V2, for I1. All right, so now we have I1. That's great. Once you have I1, you get I2. That's perfect. You could also If you want to solve for I3, you could solve this equation right here, and you solve it for I3, and delta V1 minus delta V2 divided by R3. Now you get I3. So this is fairly easy, straightforward. You could use the other equation that I showed you. I have seen students in the past use that to solve it as well, and you'll get the same numerical answer. But this one is probably the quickest one. Uh, we apply the loop rule, and the loop rules in this case, because we have two batteries, was this convenient enough. For your other circuits, basically you're going to have one equation from your loop rule, one equation from your junction rule, and then you apply your knowledge. Now, like I said, you don't have to apply these steps in this order. Sometimes you could apply the junction rule first and the loop rule first, and these things. So you could write these equations in different orders. But I feel like the 1, 2, 3 step method gives you at least some order in your thinking. And typically, when you follow the 1, 2, 3 step method, at least for like the more complicated circuits like our last one, I'll go back to it. It just makes the math look nicer, right? Because when you're always kind of working back to this loop equation, so it just logically, for me, it makes sense to use this 1, 2, 3 step method, right? You do your loop rule first. This is your main equation. You're going to try to get everything in terms of this main equation. Then you do your junction rule. And then you apply your knowledge, right? Keeping this in mind on what you're trying to get everything in terms in. For our case, is R4. That's why I picked the middle loop, because it makes it look nicer, right? So if I pick this and call this equal to that and that, I feel a little more sense of security knowing that I'm going to easily know how to work this out. Um, that's a good strategy if you're not very strong with your algebra, and you want to see some consistency, because there's many different ways you could solve these problems algebraically, right? So there's so many different combinations of equations you could come up with, but trying to lower down that combination will give you less anxiety when you're taking your test. You will have a method. So I highly recommend this 1, 2, 3 step method, especially if algebra is not your strong suit. It gives you a guidance of what to do. Um, as you can see, like in example 4, there's clearly we didn't use the junction rule per se. So there's sometimes, and we didn't just get one equation for the loop equation. We got two. So it's a general rule, but it's not always the case. So keep that in mind, that you could see some circuits where, it's you're using the loop rule or just a junction rule, um, and you're using it in a way where you might have two loop equations or things like that. So if you have any questions, please feel free to come to my office hours. But with that, you should be pretty well set up for your lab. So please, um, if you have any questions, send me an email. Thank you and have a wonderful day.